On the back of the Human Genome Project, which set to map the entire human genetic code, came the Cancer Genome Atlas. Launched in 2006, it sought to catalog the gene alterations that underlie cancer. Some 20 years on, it stands as a symbol of a tremendous and expensive genetic war on cancer. A war that we still don't look much closer to winning. Author of the Cancer Code, Dr. Jason Fung would likely suggest. As it were, over this period of targeting cancer genetics, cancer somewhere actually overtook heart disease as the leading cause of death for those between 45 and 64. That said, where an overfocus on nature, that is, the genetics, may have let us down, a renewed focus on nurture, that is, our environment, is opening up hope. Today, Dr. Fung highlights the factors we can influence to bring down cancer risk. Diet being an obvious example, with obesity now linked to as many as 18 different cancers. Dr. Fung is a physician and a nephrologist, a specialist in kidney health. He's also the author of #1 bestseller, The Obesity Code. What is the link between obesity, diabetes, and cancer? How important are the BRCA genes to breast cancer prevention and treatment? And where the seed of cancer is embedded in our genes, how do we change the soil to prevent it growing? Welcome to Vital Signs, where we learn how to get healthier from all angles, from the biochemical and nutritional to the things we do that nourish our minds and our souls. I'm Brendan Fallon. Dr. Fung, great to have you join us on Vital Signs again.
Thanks for having me here.
I know you've pointed out in your writing that the billions of dollars that have been spent in cancer research and development over recent decades, particularly on the genetic side. We're going to look at that today in part. I'd just like to start, though, in general, where would you say we stand at this point in time in terms of our ability to prevent and treat cancer?
I think we're sort of on this, just at the beginning of understanding cancer in a whole different way. Because if you don't understand what a disease is, then you can't come up with really very logical treatment. So if you understand diseases are caused by bacteria, for example, which was a big breakthrough, then you say, okay, how do I kill these bacteria that are causing this disease? And you get antibiotics, which is a sort of massive breakthrough. So the idea is that cancer is not, any like any other disease that we know of. It's not purely a genetic disease. And in the last 10 years, there's actually been really very few. Immunotherapy has been the one that's really had the most impact. A lot of these gene therapies that really have had minimal or no impact on that disease, because that paradigm on which they're based, which is let's change the genes, doesn't really work. But this paradigm of, let's treat cancer as this sort of speciation event or infectious disease, and let's see what we can do about it. That is a much more promising avenue to go, because it gets to the heart of what that cancer is. So even if you have the same gene, can you affect the environment, the soil that it's sort of living in? So you can't just say cancer is bad luck. You have to say, well, what is it in our environment that is feeding, that is leading, that is fertile soil for this cancer seed? And so stopping smoking was a very important thing. But it turns out that the second most important thing, so if you look at the things that cause cancer, you can do these big studies, and you can attribute risk. And the most important thing is really smoking. But the second thing was actually diet and obesity. By far and away was those two factors were about 30% of cancers, compared to, like 2 or 3% for everything else. And that's all the other things we think about: chemicals and herbicides and pesticides and radon gas and asbestos and all these other things that we think about as carcinogens actually paled in comparison to tobacco smoke and diet.
I did understand that diet and obesity were factors in influencing cancer, but I didn't realize how high it was in the hierarchy.
Breast cancer is one of the obesity-associated cancers. So as you have more obesity, then the risk of cancer can go up. So if you have that original gene that puts you at higher risk, now can you go backwards? Can you now affect people so that you don't always have to cut off the breast or, take out the prostate or whatever it is? Can you affect it? And part of it is because insulin is, people who are overweight or obese, they have high insulin levels. For example, that's part of the disease, and the high insulin levels acts as a growth factor to a lot of these cells. So if you can then change the diet or change their weight, which we can, then can you change that risk so that it's lower than before, right? And that's and you can't, we don't have all the answers right now, right? But perhaps we'll be able to do something more specifically in the future.
Interesting to hear insulin mentioned there, Dr. Fung, because many people would think insulin and just think of it as something that's used to manage their type 2 diabetes. So it's a revelation to know that it actually works as a kind of growth hormone and can trigger tumor growth. How does that work exactly? And could you elaborate on that? And what is the solution to dealing with that?
So insulin is a normal hormone, and we all think of it as a hormone that's important for metabolism. That is, if your blood sugar is high, you take insulin and it goes down. But insulin is actually a growth hormone as well. And the reason that they're linked is that your body really only wants to grow when nutrients are available. So the way our body has sort of linked the two is that when you eat, insulin goes up, and insulin then acts as a growth factor. So if you give people insulin, they tend to grow. So for example, if you give mothers insulin, their babies tend to be very, very big, because you're giving them not just something to control their sugars, you're actually giving them a growth hormone, if you will. So the idea is that if you have a disease where things are growing too much, well, giving them insulin is like giving them fertilizer, right? It's going to speed up that growth. So it's not the only factor that's at play, of course, but it is one factor that is relatively important. And it's chronic damage. If you have any chronic damage to a cell, chronic long-standing damage, you need to get rid of it. And anything that causes chronic damage to cells can actually cause cancer. You actually see it even with chemotherapy and radiation. So even the very things that you use to cure cancer actually cause cancer. And so the initiating event is this event of chronic sort of damage that's happening, chronic inflammation, for example, that's happening. And then the thing that's going to promote it is this high insulin level. So people who are overweight have high insulin levels. People who have type 2 diabetes have high insulin levels, sort of on a chronic basis. It has to be on a chronic basis for many, many years. And this is what's happened. You see with type 2 diabetes that there's a strong association between that and certain types of cancer. In fact, it's very clear that diabetics have a much higher risk of cancer. So then what can you do about it? Well, you can adjust your diet. So if you adjust your diet, then you're going to have lower insulin levels, for example. So if you change your diet so that you're not eating foods that stimulate a lot of insulin and you lose weight, then you're going to affect your risk of cancer, because you're providing a less fertile soil for that cancer. It's not like one of these, 100% you're not going to get cancer things, but it's going to play a role in it.
With everything that we're discussing here, I think it prompts the obvious question, is obesity causing cancer?
And the answer is yes. And this is actually well established. In fact, in the 90s, we didn't even know about this, which is sort of stunning. It wasn't really until about 2000, 2001 that a couple of big studies came out that clearly linked obesity with cancer. And that's a big problem for the somatic mutation theory, for example, because being obese doesn't cause gene mutations, right? It's not mutagenic. Why is being obese an increased risk for cancer? And not just a small risk, a huge, massive risk. If you look at the World Health Organization, they classify 13 different types of cancer as obesity-associated cancers. And this includes really important ones like breast cancer and colon cancer. The one that's not, of course, is lung cancer, and that one is mostly associated with smoking. But obesity plays a huge role in that. And of course, obesity has nothing to do with, it doesn't change your genes, it doesn't do anything like that. What it does is it provides that fertile soil for cancer to grow. In 2000, 2001, some of the first studies came out that showed that being obese clearly increased your risk of all these different types of cancers, pancreatic cancer, kidney cancers, in some cases by a lot. Like, you aren't talking about, the 5% increased risk. You're talking about double, triple the risk of somebody who's not overweight.
Shortly, we'll look at whether we can really inherit cancer, and we'll learn how discovery of the BRCA breast cancer genes have influenced breast cancer's outlook. But first, on the topic of changing diet to lower obesity, diabetes, and potentially cancer risk, here's a look at my earlier interview with Dr. Fung. I've heard on that eating bread would spike your blood sugar more than drinking Coke.
Oh, absolutely. If you have this white bread and jam, you get this massive spike in glucose. You feel good. But then by 10:30 in the morning, it's starting to go below normal. Then you're going to start to feel, you're going to be shaky, you're going to be hungry, you're going to be sweating. So these massive glucose spikes are actually really bad for you. Using simple versus complex didn't tell you how quickly it got digested. What you do want to do is avoid the rapidly digested carbohydrates. However, it doesn't mean the Coca-Cola is better for you. It has fructose rather than glucose, so fructose is actually much more dangerous.
How is that the case that we would see comparatively better health in Asia despite that high-carb diet? Afterwards, find the link to that video at the top of the comments and also in the video's description below. And to get notice of new Vital Signs videos, follow me at Vital Signs Brendan on Instagram and Facebook, and at C Vital Signs on X. So far, I think we've focused on the nurture side of the nature-nurture debate in terms of cancer, looking at environment and dietary changes and things like that as a way to reduce cancer risk. I'd like to switch to looking at the nature side a little bit in terms of genetics. I know that you've spoken about not tremendous results coming through from the amount of focus that's been on genetic research, but I know with the BRCA gene mutations for breast cancer, that these have been used to some considerable success as a way of detecting breast cancer risk. So what about that case? Is that an exception to where the genetic side is yielding results?
Yeah, so it indicates, so you have the BRCA1 and BRCA2 genes, which were identified as important to increase your risk of breast cancer. The problem is that it doesn't lead you to a useful treatment. If you have breast cancer and you have this gene, well, now what do you do about it? Well, nothing. You just treat it the way you normally do. So that's not that useful. You can identify somebody at risk, and then some people will elect to have, say, mastectomies, but that's a very crude way of treating the problem, right? So you have a risk of breast cancer, so you cut off the breast. And people have done this. Angelina Jolie, for example, was a very famous person who started speaking out about this gene. But it's a very crude thing, right? So you haven't targeted the gene. What you've done is you've gone back to the sort of growth paradigm and simply cut off the entire tissue. So if we go back and we say, okay, originally the way we understood cancer was that it was simply a disease of excessive growth, right? So you have a breast cancer, for example, or a liver cancer or whatever kind of cancer, and it grows and it grows and it grows until it basically pushes everybody out and it destroys other normal tissues and then causes all these problems. And it's a disease that spreads. And again, that's not typical of any other diseases. So if you have a breast cell, it doesn't go anywhere else, but a breast cancer cell will go to the bone or will go to the liver and cause metastases. So the initial way we understood cancer was simply as a disease of excessive growth. And that led to various treatments, which were quite successful. So surgery, for example, is a way to cut out that excessive growth. You can also, give radiation. So you can burn these cells that are growing too much, right? So you use radiotherapy. And that was very successful too. And then you can also poison them with chemotherapy. So chemotherapy, the idea is that you kill cells. You kill the rapidly growing cells a little faster than kill normal cells. That's why you have so many side effects, because you're killing a lot of cells. So that was the way we understood it. In the 1970s, 1980s, there was then this whole understanding about genetics. So the question is, okay, so cancer disease that grows too much. Well, why is it growing too much? That it couldn't answer that question. And that's where the sort of genetic paradigm of cancer sort of came into focus. And the genetic paradigm of cancer was sort of this idea that, hey, why are these cells growing too much? And it's because the genes that are responsible for growth are overactivated, right? So that's the explanation. So there are genes that cause cells to grow and they get overactivated. There's genes that cause cells to stop growing and those become inactivated. So it's like sort of like either hitting the accelerator or taking your foot off the brake. Either way, you're accelerating this growth. And that was a genetic paradigm. And that's really what's been with us for the last 25, 30 years. So there were several treatments, for breast cancer. There's Herceptin, for example. That was really a game changer for some of these diseases. And so everybody got very excited in the 90s, for example, as this sort of the tools of the genes and stuff got more understood. And we sort of understood cancer as this genetic disease, as a disease of genes that got activated or inactivated is due to mutations in these genes and so on. And that's the way we looked at things. The problem is that the wheels quickly fell off. So in the 90s, people thought that, oh, okay, this is great. We're going to cure cancer. What's going to happen is that we're going to take a cancer such as colon cancer. We're going to find the 2 or 3 gene mutations that are responsible for colon cancer. We'll just devise a way to fix those genes and then we'll cure cancer. But very quickly in the 2000s and 2010s, it became clear as we sort of sequenced the human genome and went through this whole thing that it wasn't simply a few genetic mutations. It was hundreds of mutations. So breast cancers and other common cancers, they didn't have 1 or 2 gene mutations. They had hundreds and hundreds of gene mutations. And the problem is that as they started to catalog these genes, the number of genes, a few years ago, I looked at this, and the number of genes that were found in cancer cells was somewhere around 6 million. You can't fix 6 million different gene mutations. You can't come up with 6 million different drugs. It just doesn't work. And that was sort of the starting of the downfall of this sort of genetic paradigm as a useful way to think about. The initial genetic paradigm, which was called the somatic mutation theory, was that it's sort of this random thing. Gene mutations happen all the time, and as you get older, you get more mutations. You accumulate these mutations. If it happens to hit a critical growth gene, then boom, you get cancer. Then there's this 2-hit hypothesis where it's like, oh, it's just not just one mutation in this gene. You had to have 2 hits and then you could get it. Turns out you probably needed 50 or 100 hits. So the question is this was not merely random, right? The whole somatic mutation theory was that this was sort of semi-random. It was just a random sort of luck thing. It was just bad luck that these genes happened to be mutated.
And being influenced by the hereditary as well?
There is a certain hereditary basis, but most of cancer is not hereditary. That is, a lot of people develop cancer, and certainly if you have a relative that has cancer, you're at higher risk of cancer because their genes are going to, just like if your parents are tall, you're more likely to be tall, right? It's sort of one of these things, but it's not like sickle cell anemia, where, for example, if you have 2 parents with sickle cell anemia, then your child 100% is going to have sickle cell anemia, right? So it's not genetic in that strict sense. There is a genetic component to it, as there is a genetic component to everything, right? There's a genetic component to risk of obesity, risk of diabetes, height, weight. Everything has a genetic component. But cancer wasn't strictly a genetic disease in the way that polycystic kidney disease or sickle cell anemia or thalassemia is a genetic disease where you can find the specific gene. That's what we thought cancer was going to be. You find the specific gene, the BRCA1, and then you're going to be able to treat it. It wasn't that, because there's millions of different mutations and hundreds of genes involved here. So that was sort of, it didn't lead to as much useful treatment as we thought it is. And that's ultimately the test of a useful paradigm. It's not that the genetic paradigm was wrong. It's just that it didn't come to the final answer. So the growth paradigm, which was the sort of first iteration, was sort of like genes, cancer is a cell, is a disease of growth. The question is, why is it growing? And it's like, okay, well, you have gene mutations. Well, now the question is, why are you developing these gene mutations? And that's the sort of next step in understanding, and hopefully will lead to treatments. There may be more to come, but it's a sort of fascinating field The interesting thing about cancer, which is so frustrating, is that it's a disease that develops from our own cells. So that breast cancer cell was originally a normal cell that somehow, for some reason, mutated. And the evolutionary paradigm, the next step is to find out, what is driving these mutations.
Dr. Fung, thank you so much for coming on and highlighting these exciting and hopeful shifts in the way that we think about cancer.
Thank you so much.
In Cancer Code Immune Shield, Dr. Fung reveals how this new concept of cancer, which sees cancer as a type of infectious disease, is paving the way for powerful treatments like immunotherapy. Let's take a quick look.
So what cancer is not in fact a random genetic mutation. Well, you're subjecting that lung cell to chronic damage, and it says, I need to survive, I need to survive.
Is survival the driving force of cancer's mutations? What factors allow cancer to take hold in the body?
There are hundreds or even thousands of cells that are constantly undergoing this cancerous process. And the reason that you don't know about it is because your immune system has basically mopped it all up before you even knew about it. We couldn't even detect it.
What power lies within our own immune system to bring cancer to heal? Tap the link to that video at the top of the comments or in the description below. Also there is the link to Silent Sugar on which foods to eat and which to avoid to stave off obesity, diabetes, and potentially cancer. And that one is also with Dr. Fung. You can subscribe to access these and other news and health insights by clicking the big red button. It's been great to be with you. I'm Brendan Fallon, and this is Vital Signs.